Welcome back. Now we've just found the general solution to our dampened simple harmonic motion under the condition that it was lightly damped and that the restoring force was in general greater than the damping force. So we found that our general solution looked kind of like the solution for the simple harmonic motion in that we had a sum of sine and cosine. But the only difference is now we have a different frequency, a different value of omega, and now we're multiplying this by a decaying exponential. So let's see how these two things impact our solution and overall impact what the system looks like. So let's get started, and let's first talk about the amplitude. And the way we're going to do that is let's first just draw out a normal undampened case, basically just plotting out c cosine omega t minus phi. It's going to be a simple sine wave that's going to look something like this. Basically it goes between plus c and negative c, and it oscillates like that forever. You can think of it as being bounded between the lines x is equal to plus c and x is equal to minus c, because it can't be greater than plus c and it can't be less than minus c. So now let's draw out the full general solution. We still have a cosine though, so we're still going to have some like oscillations in here. But the way you can think about it is, you can think of our amplitude as exponentially decaying. Our amplitude is going to get smaller and smaller and smaller as time goes on. So it should look something like this. Let's see if I can draw this right. It's going to start off looking normal, and then the amplitudes are going to get smaller and smaller and smaller, and eventually they're just going to flatline. And that kind of makes sense if we think about it from like a physical system perspective, like a mass and spring that's experiencing drag. We know that the oscillations are going to get smaller and smaller, and they're eventually going to stop. So this is what this function here is describing. But the key thing to keep in mind is that the amplitude is exponentially decaying. In a way, you can think of it as here, our cosine term was bounded between plus c and minus c, whereas here, our cosine term is bounded between two exponentials. We have plus c times e to the negative gamma over 2t, and minus c times e to the negative gamma over 2t. So it's kind of like a cosine term that, as they say, is trapped between like this envelope here. So that's what's happening with the amplitude. Now let's talk about the frequency for a bit and compare that to simple harmonic motion. I have it written up here, but I'm just going to rewrite that we found that omega was equal to the square root of omega naught squared minus gamma squared over 4. And we had said that omega naught, that was our natural frequency. And that was defined as the square root of k divided by m. This is the frequency that the system would oscillate with if there were no damping. And we found that this was the frequency in like the first couple of videos on simple harmonic motion. So now let's see what happens when we add damping. Essentially, we can look at that more directly by factoring out an omega squared from under the square root. So we get that omega is equal to omega naught times the square root of 1 minus gamma squared over 4 omega naught squared. And the reason why I want to put it in this form is it's much more easy to see that here we have a term that's squared, so this is going to be positive. Here we have another term that's squared, so this is going to be positive. So this entire term is going to be positive. And since we know from the condition that of our underdamped case that omega squared over 4 is less than omega naught squared, or you can think of it as omega squared is less than 4 omega naught squared, we know that this is going to be a fraction, a positive fraction, which means when we have 1 minus this positive fraction, we're going to get something that's less than 1. So this entire square root thing is going to be less than 1 for the underdamped case, which means when we multiply it by our natural frequency, we get a frequency that's smaller than our natural frequency. That's the main kicker. It's smaller than our natural frequency. We undergo less oscillations per unit time. And that kind of makes sense, because if we were experiencing some drag, you can understand that it wouldn't oscillate back and forth as quickly. So the two takeaway points are that the amplitude decays with time. The frequency is smaller, but it's still constant. It doesn't decay with time. It's just smaller than before. And those are the two hallmarks of lightly damped simple harmonic motion. Now, let's just do one quick thing. We can do one quick exercise and say, what would happen if we had no damping? Would we be able to recover our original solutions for simple harmonic motion? And no damping, that would correspond to b is equal to 0, which would mean that gamma is equal to 0. So our solution would be x is equal to e to the negative gamma t, which is just going to be e to the 0 power, times a cosine omega t plus b sine omega t. And we know that e raised to the 0 power is just 1, so we get the typical solution like before. Likewise, when gamma is equal to 0, we know that the frequency will be the same as the natural frequency. Because if the frequency omega is equal to the natural frequency times this mess, 1 minus gamma squared over this, when gamma is equal to 0, we find that it's just the natural frequency times radical 1 minus 0, or just the natural frequency times 1. Essentially, we get that the frequency is equal to the natural frequency. So we found that essentially, if there is no damping, then this term will give it, this more general solution will simplify back down to the solution for simple harmonic motion. And that's lightly damped simple harmonic motion. We pretty much covered all the points. These are the general solution for it. This is what it looks like. This is what's happening with the frequency. And we know that we can recover our original solutions under the idea that, under the condition that their gamma is equal to 0. Let's take a look at in the next video we're going to take a look at another case for as a solution to this differential equation.